A stick of length L, it's a positive constant, is broken at uniformly random points given by the random variable x. Given that x does break at little x, another breaking point is chosen uniformly on the interval up to x now. So we're asked to find the joint PDF of x and y, and we have to specify the support here. So looking at a stick, let's just draw out the stick and see what this means. So we have a stick, it has length L, and then we're breaking it. I mean, x can operate at any point this interval. Let's assume it was broken here, large x set little x. Now y can only take points in this interval here. So y, just to be specific about the support, so y is conditional on knowing x is distributed uniform from 0 to little x, and x is uniform from 0 to L. Okay, and the joint PDF of x and y, what is that? So that we can write, so we could think about it by using Lotus, because I mean it's a useful fact to know x here, right? That's so we want to condition on it. So using the law of total probability, we can write little y, conditional on x, conditional on f, and because these are uniform, we can then now we know that the uniform, any uniform, has the value is its inverse of this length. So this is 1L, this is 1x, multiplication there. So the joint PDF is exactly what we have written there. And so just to be clear now that y can only take values between up to x, between 0 on x, and L. X on the other hand goes up to L, and it can be as little as 0 here. Okay, so let's now find the Alright, so we already know the marginal distribution of x. Yes, that's the uniform. We're asked to check that marginalizing out actually yields what we know. So basically assume that we don't know what the marginal of x is. So marginal of x, now we are asked to integrate out y from the joint x, y with respect to y. We now check what this number yields. So that recall what does, and we know obviously what we just calculated what f of xy is, but what's the support of y? Well, the support of y is 0 to x, so we have to integrate over this area, and we have the joint PDF was just exactly that, and now we have no y's here, so we can treat 1 divided by x, 1L, as constants. So we go from 0 to, sorry, so this says obviously not to y here, it should be to x, like so. And this ends up being 1 divided by L, 1 divided by x, multiplied by x, minus 0. And here we can divide these two out, and we get 1 over L, which is exactly the marginal of x here. Good, so that makes sense. Let's see what the third question has for us. And again here, we already know, given this text, that the conditional distribution of y given x is uniform, 0 to x. But we're, again here, asked to check whether using the definition of conditional PDFs, that this agrees with what we know. All right, let's do that. So C, we want to know what the PDF of y conditional on x is. That we write as, so actually let's use another notation just to be very clear about what we're doing. Y, write it in here, write it like so. And then we have to divide by f of x, f of y x. Okay. So here we know what those two numbers are. We just calculated them before. So f of x we know is 1 divided by L, and the joint is this number here. So we're going to copy it like so, and we can immediately see that we can cancel out these terms. We end up with 1 divided by x, which is precisely what we said that this uniform has of a PDF. Okay, that's reassuring. Checking now the fourth question, we asked to find the marginal of y. And the marginal of y is a little trickier because it's sort of going in the other direction. And in this process, we're asked that we have a length, sake of like L, then we choose X, and then after that we sort of sample Y. But here we are asked to find the marginal Y basically starting at the end point of this process. Okay, so let's write it down. See what we, following the definitions. So f of y, now we have to marginalize out x. So we have x like so from the joint. Now, what does this support? What is this integral integrating over? This is the, I mean, oftentimes it's really the limits that produces the most difficulties. So let's write out what the support is. So we know, let's write it here. So we know that y goes over that support, and we also know that x goes from 0 to L, right? So then y has to go from, well, basically, sorry, so x has to go from y to L in order to fulfill this condition so that we respect the support of y. Okay, so we then marginalize over y up to L using the PDF of just going up here and copying it just to remind ourselves what we are looking at. Copy that, so d of x. Okay, and here we have we can treat this term a constant. 1 over x is actually the natural logarithm, so that's the so if we take the derivative of the natural log, we get 1 divided by x. So this is calculus now, and we are integrating over this support, and we shouldn't forget the 1 over L, 1 over L, and this is now ln of L minus ln of y, like so. And that is the marginal of y. Now, just checking my notes, but this is basically it. In the last part of this question, we are asked to, let's see, we are asked to find the conditional of x given y. Okay. Again, this sounds also in terms of the process that was described, so going in the other direction. So we're asked now probability, not the probability, it's a continuous variable, so it's PDF, so x conditional on y, and these should be little x's, so just and little y's, just to be absolutely clear. Okay, and here we can rely on what we've calculated. So f of y we just calculated, and x and y we have been using all along. So 1x, 1l, and dividing it by this whole term here. Duplicate that, we put it in here. Great, and then we see that we can simplify this further by subtracting off, factorizing out those terms there in the end. Okay, so, and what is this support valid for? The support has to go from y, of the support of x, y, up to x, up to L, which is exactly what agrees with this original support that we were given.